hopefully what I'm going to show you this afternoon is more impressive than a sight gag. Okay, but as you see, not only do I neither have sleeves, but I have nothing up my sleeves. There are no slides. To make this an extra element of danger, it's all live coding. Okay, but to set the scene, what are we going to do today? I'm going to show you 3 different types of profiling. We're going to improve the performance of 2 different programs, and we're going to do it in 43 minutes and 38 seconds. All right, so I better get cracking. So what I have here, well, let's show the code. Is that embiggened enough? All right. What we have here is a simple program to read a piece of text and count the number of words in it. We open the file, as you'd expect. We have some counters for words and a very, very simple state machine to say we're actually in a word. And so until we reach the end of the file, we read a byte, check we didn't get to the end of the file, make sure there's no other kind of weird error, and then we say, is this a space? Did we just read a space? And also, if we're in a word, because we're basically reading through the file, counting character, 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 space. Okay, that's a word, including the word counter. Now what happens if there are a few spaces in a row? The presence of a space, it's only a word if there's a non-space either side. So we have to keep a little state there. And then we ask, is it actually a letter? So let's, well, first thing, why am I building this program rather than using the more convenient Go run? Well, because we want to find out how long it takes to execute this program. We don't want to include the time of compilation. So first of all, go build this program. And now we're going to need some input. And it should probably be a reasonable size input, like you can count how many words there are in very short strings yourself. You don't need a computer for this. So thanks to the internet, we have the complete text of Herman Melville's Moby Dick, which is quite an extensive volume. And if you've ever had the unpleasant pleasure of working with me, you will know that I will take this text and drop it into any text box in your application and see what happens. How big is this? It is 1.2 megabytes of fine prose. So, actually, sorry, it's... Okay, how long did that take? Okay, I should have timed how long that took. It seemed to take some time. So how long does it take to count 1.2 mega of characters? 2 seconds. Okay, I don't know, like, is that a reasonable amount of time to take? Or is that, given that we've just run this program, we have no basis for comparison, let's compare to something else that counts words. Does anyone know a program that we can use to count words? Okay, you call word count. Is that its real name? WC, yes. Why write word count when you can just say WC? So, number of words. Well, I don't know if we need to time it. That was effectively instantaneous. Okay, for comparison, let's just compare our version. Okay, so important thing I need to point out, that there are a different number, and that is correct. What WC considers to be a word and what my program considers to be a word are not the same. But I think the underlying idea that the program has to read all the characters in the file you have to iterate over all the characters to find the spaces and count the words. So while they come up with slightly different answers, I don't think that's really important for the purpose of this demonstration of optimization. But given that we do have some challenges, we need to make this program at least 2 orders of magnitude faster. How will we go about doing this? If you're in Chris's talk here a few hours ago, we asked Dr. P-Prof. So the first thing we need to do is profile this program. Welcome to my office with the world's least ergonomic standing desk. And because I can't ever remember how to do it with runtime pprof, I'm going to use my own helper package that I wrote. And we're just going to say put the profile just in the working directory, so it's not a horrible long import, a horrible long path. Run go imports on save like everyone does. Okay, so now when we run this program, golly gosh, I forgot to defer the stop. There we go. I told you there's an element of danger. Okay. So, two things to note. One, this program has got a little bit slower. pprof profiling gets the operating system to set up an interrupt on a very frequent time. I think it's 100 times a second. And that kind of stunning the process and asking it to do some kind of profiling in the background does add some overhead. It's made it a little bit slower. But the benefit is we now have a profile. One of the nice things that was added a couple of releases ago is a much more updated version of pprof in the standard library. So we can now ask it for a visualization rather than and a nice web-based GUI. So let's just full screen this. So this is the default thing that you'll come across when you get a profile and you look at it in pprof. And there are a few things to point out here. You can think of, there are three kind of distinct starts of these trees. What you're seeing here is the call stack. So there are three kind of prominent call stacks. The way that pprof works under the hood is every time we stop the process, we sample the current call stacks of the active Go routines. And then when we get to the end of the program, the ones that show up the most are obviously the ones that were doing the most work. So one of the things you can see here are there are kind of three distinct areas. I'm going to ask you to ignore this for the moment, and we'll go back and find the bit that's actually our program. And this is our program over here. The others are both part of runtime stuff, which we'll come back to. One thing to note, the order in which, because this is just a graph you passed a dot, it can be randomized around. The position of the elements on the screen is not really important. It's the arrows between them. Normally when I run this, runtime.main is over on the other side. It's entirely random. So we have runtime.main, main.main, main.readbyte. And the important thing to see here is that they all contribute themselves nothing to the call stack, the time of the call stack. 0 seconds of 1.4 seconds. Passing down into file.read, 0, 0, and just all of that time is passed down. Through some FD stuff, syscall.read, syscall, and then we get to the big contributor, syscall.syscall. We had an issue on the Go project, which actually inspired this, where someone wrote in and said, syscall is too slow. Look at it, it's huge. It's consuming all my CPU. You must make it faster. Like, what are you doing? You're amateurs. Do you think that syscall is too slow? I was expecting either like a yes or no to that kind of. Okay, so it wasn't that I prompted you for the answer, but if syscall is not too slow, then what is the problem? It is using all the time in our program. But why? Too many syscalls, yes. Why would there be too many syscalls? Exactly. It's not that syscall is slow. It's that in Go, all our read and write operations are unbuffered by default. We don't have a kind of buffered abstraction by default. If you want buffering, you should buffer yourself. Now, I ask you to ignore this. This tool always presents so beautifully, like it's so easy to show on a screen. So if this is this arm here, and maybe I can demonstrate with technology, if this arm here is the work of our program, then what's all this nonsense over here? What's happening over here? It's a lot of runtime stuff. All of them end up in like pthread cond wait and cond signal. If you, again, were at Chris's talk, this is what he's talking about, the overhead of handoff between threads. It's quite expensive to sleep one thread and wake up another. And one of the reasons why this can happen is, you notice that in syscall.read, it's called syscall.read, but it then dispatches to a generic syscall.syscall. So from the Go runtime's point of view and the operating system underneath it, they're all just syscalls. Whether you're asking for the time, whether you're reading a file over a network connection, we don't know how long the thread underlying this Go routine is going to be gone off in syscall land. So what happens under the hood is the Go runtime has a timer, and if that timer elapses before the syscall is returned, it's time to panic and make a new thread to make up the pool of threads that service Go routines. If the syscall does return fast enough, then that's okay. Like that latency we can just hide. I think the timer is like 20 microseconds at the moment or something like that. It's pretty small. So what we're seeing here is we're spending so much time in syscall that the Go runtime is having to replace that thread which went off to do a syscall with another one to make up the difference. Every time you come back from syscall, now there's a thread that's supposed to be in the scheduler and an extra one that just is hanging around. And so what I believe most of this overhead is the constant chopping and changing and switching and going to sleep and handing off between them, which of the several threads in this program is actually responsible for it. But let's come back to the problem. So, how do we fix this? We buffer it. Okay, previously it was 2.6 seconds. Let's see how long it takes now. Impressive. So that one change improved the performance of this program by an order of magnitude. Let's have a look at the CPU profile again. Let's do it properly. Okay. Now, not only has this changed, but we can't even really see our own program in here anymore. There's like our main.main and all the code that we're actually running is not visible anymore. There's just some kind of just runtime stuff. And you have to note that the times are very small here, 30 milliseconds, 10 milliseconds. This is because, again, profiling is triggered on a periodic basis. If the program doesn't run for very long, we're not going to make many samples. It only ran for 0.2 of a second. It probably only took 20 samples. Probably took less. So what is the histogram when all of the samples are different? Well, it's basically random. So the CPU profile is not telling us anything really useful anymore. Like this is just background noise. Well, there is one thing. It doesn't show it here. Again, it really depends on, because we have so few samples. But in times when I run this, sometimes it points to malloc GC. So of the few stack traces it was able to grab. And in fact, let me just try. I mean, this program takes so little time to run anymore, we can just grab another profile it. Yes. So now, I mean, even though, like, this is just one sample, 10 milliseconds, but it's saying that of the activity I could grab, malloc GC. So maybe memory usage is a key to the difference between what WC is doing and what our program's doing. So by that setup, it gives us a hint that we should try a different kind of profiling on this program. So let's switch from CPU profiling to memory profiling. And now when we run our program, rather than capturing CPU cycles and using an interrupt from the operating system, the Go runtime itself is going to catch the stack trace that led to that allocation. And you see here it says rate 4096. By default, we don't sample every allocation, we just sample 1 out of every 4,000. And let's have a look at that profile now. You can also see that the real time went down significantly. So different types of profiling have different overheads. In fact, now we're not using that operating system interrupt. The overhead is quite a bit lower. So we can look at this profile just like we did the CPU profile. And what it's telling us is all of the allocations in this program are coming from main.readbyte. And we can actually, rather than looking at it graphically, we can actually see the source code, and it's telling us the line that the allocation is coming from. Now, there's one thing I do want to diverge on just a little bit and show you. See, it says 617 kilobytes. This is because we are sample-based. We're only sampling 1 out of every 1,000 allocations. We can, at the cost of some performance, crank that rate up and say, I want to profile every allocation. Okay, you can see there was an increase in the overhead. We increased the overhead a little bit, but we've also set the profiling rate to 1. So now when we look at the profile itself, we should see every allocation that happened in this program. And of course, we see read byte up there, and we see read byte up there with 1.2 megabytes. So that's a really strong clue that the memory usage of this program is directly derived from the data you feed it. You feed it a 10 megabyte program, it's going to allocate 10 megabytes of memory. The other thing is that there's our 1.2 megabytes. We know this is exactly where the allocation is coming from. So, can we fix that? What's a way that we can... I should explain why this is leaking. It's leaking because we declare an array, we slice that array into a slice, and we pass it to read. Now, what is the type of R? It's an I reader. It's an interface. So the runtime and the compiler don't know at runtime what reader we're actually going to be passed. Could be a file, could be a buffer IO, could be something that somebody else has written. So we don't know what they're going to do with the contents of the buffer that we pass them. They might capture the address of one of the elements in the buffer and keep it for why they know. So this forces this allocation to escape to the heap, and that's where all the memory allocation is being reported. So, in the interest of time, one of the ways that we can solve this is just to do that. Now, instead of allocating a buffer on the stack which escapes to the heap, every single time we call read byte, we're just going to reuse that buffer, reslice it over and over again. And now, that's more what we expected. 0.2 of a second. Let's just compare with WC. Pretty close these days. Let's have a look at the profile. Let's just compare to the previous one, which I can't do. Yep, I can't do because I've closed the terminal. And it might look like I've made it worse because there's an awful lot more on the screen now. But if you actually zoom in and find out what these allocations are, they're tiddly, they're tiny. In fact, the biggest allocation in this entire program is the 4K buffer for buffer IO reader. We've reduced the allocations in this program, so now things that were previously tiny below the threshold of visibility have now bubbled to the top. And in fact, if we look around here, one of the cutest things I like about this is that you see the allocations for printing out the log line that says your memory profile is here. And just for completeness, let's turn off all the profiling. So we're now around about twice as slow as WC. And I think that's a pretty good result. We don't have time to argue about like what it would take to get down to WC's level. But the thing I want you to take away from this is knowing nothing about this program, using only the tools in the Go standard library, we were able to improve its performance by 2 orders of magnitude. Now, maybe in all programs there aren't this many pieces of low-hanging fruit, but this simple investment of time, I think, pays off for anybody who's interested in improving the performance of a program. So I promised you 3 different profiling methods. So we're going to leave this example here, and we're going to move to something different, which is an example that both Francesc and I work off. This program, when you run it, produces a Mandelbrot image. People are probably familiar with this kind of fractals. They were very popular in the 90s when I was a child. It produces a thing like this. This image has 1024 by 1024. This is a megapixel. This is 1 megabyte of pixels that we have to compute. So how long does it take to do that? Let's do a quick sniff test. 1.6 seconds. On this day, at this altitude, with this temperature, don't forget, laptops run slow when they get hotter. So today, it's 1.6 seconds. Is this good? Like, I don't know, like, is 1.6 seconds to make a megapixel image? Like, think, when was the last time you had a camera with a megapixel? Like, so maybe using 2019 hardware, 1.6 seconds isn't great. So let's apply the knowledge we just did with the previous program and see if we can improve it. If I was really smart, I would have set up macros for all this. But there we go. So exactly the same as we did with the last program. Grab ourselves a CPU profile. Let's have a look at it. Okay. There's a bunch of stuff here. There's some runtime stuff. It's all very small. When you're reading these graphs, you follow the arrow. You follow the giant arrow, and it tells you where most of the time is being spent. And this is telling us that main, something called sequential fill image, and fill pixel, and paint are taking nearly 90% of the time. So don't worry about anything else in this graph, because if we don't fix this, we don't improve the performance of the code. Let's have a look at the source. So this is paint. It's just a little function that takes the Mandelbrot calculation is you iterate over a complex number until you reach some limit. And you take that limit and you use that as the color of the pixel. So we're doing that here, and then we're assigning it to the red, green, and blue. So paint is just assigning to some fields. Don't think we can speed that up very much. Fill pixel is the Mandelbrot equation. It runs that until it reaches the limit, and then we hit paint. So pprof told us what it saw. It said, you're using all your CPU time here, but I don't think we're going to be able to improve the speed of assigning to a field, and I don't think I'm smart enough to compute the Mandelbrot equation faster. So it seems like pprof has told us what it saw, but there's not much we can do with that information. So this is now the case to introduce a different tool, which is the trace tool. Now, tracing was added in Go 1.5, and over the next couple of years, we actually figured out how to do it. We uncovered the missing manual of trace. So asking for a trace profile rather than a pprof is just as simple as asking for a trace. Now, we use a different tool to analyze this because it actually reuses a bunch of infrastructure from Chrome, as it turns out. So this thing is just running a little web server, translating our trace file into the output that Chrome wants to visualize. This is the JavaScript debugger. Super useful tip, question mark shows you the hotkeys. Just like on every other Google property. So using those, A and D go left and right, W and S zoom in and out. What can you see on this graph? Like there are three things that are very obvious. The first one is that this program is bimodal. It does some stuff here, and then its operation changes. I'll just zoom in there. Its operation changes, and whatever this is, we'll get into what that is in a second, it behaves differently, it moves around. We can see this is a graph of the heap, which is very common for garbage-collected languages, this stair-step behavior. So obviously, memory allocation is involved here, like it starts to allocate memory. Now, we can explain what we see here, because don't forget we compute the image and then we write it out. Let's have a look at if I have any of these left. Nope, I don't have any of them left, that's okay. So this is obviously computing the image, and then this is writing it out. And in fact, we can prove that by if you click on these and you're lucky, you actually get a stack trace for them. There we go. Main, PNG encode, write, compress, write out. And there's one glaring thing on here. Does anyone want to take a guess at why this program is not as fast as it could be? Yell it out. Single-threaded, yeah. There's a big green line here on proc 0, and all the rest of them are doing nothing. So, one of the ways that we could improve the performance of this code without having to reinvent a new form of mathematics to multiply complex numbers is to just spread this work over multiple CPUs. And that's in fact what we can do with this program. This is our sequential fill image for each row and each column in each row. Compute the pixel. Now this is Go. We have Go routines. Why don't we just compute every pixel in parallel? So for each row, for each column, start a Go routine to compute the pixel. Now, of course, we can't do 1 million pixels at the same time. There are only a limited number of cores, but we know the scheduler handles is built for this, so it should, we'll work through that backlog of Go routines as quickly as we can. And the way that we do this program has a mode flag, so we're in sequential mode, we can go to per pixel mode. Okay. So it didn't really change the time, 1.6 seconds to 1.7. One thing that did change was user. Real is the real time. It's the time that we experience. It's the progression of time. User is an accounting measure for how many CPU seconds are used. If we use more than one CPU, we use time at a faster rate. So given that they were the same here, but vastly different here, there's a hint that we're doing more parallelism, like we're using more CPUs. But also, it didn't seem to make the program faster. So let's have a look at the trace. Now, it's taking longer to load because the size of a trace is based on the number of Go routines and their interactions. So we used to just be single-threaded. Now we have 1 million Go routines all fighting to get on the scheduler to do their work. And this really does chug quite hard. And because of this, when it opens, we won't be able to look at the whole 1.5 seconds of the runtime. We have to kind of break it down into smaller chunks because just loading all these points into Chrome's debugger is not a good idea. It really chugs doing this. Now, okay, so there's more work on more cores, but there's a lot of gaps. And something else that I want to point out is the idea that we had, what I suggested was, let's start all those Go routines and then just sit back and wait for them to finish. So we have a count up here of the number of runnable Go routines and the number of running Go routines. Now, I was expecting, runnable is ready to run, so I was expecting hundreds of thousands. But there's only like 6. Like, it never seems to get started. And if we zoom all the way in here, we can see that like there's virtually no work happening at all. In the interest of time, what I believe is happening here is that the amount of work it takes to compute 1 pixel is very small relative to the overhead of starting and managing those Go routines. And in fact, don't forget that the producer itself is a Go routine. It competes for CPU time with the things consuming them. So if all your CPUs are busy computing pixels, there are no threads available to start more Go routines. So if doing 1 pixel per Go routine is too small an amount of work, what if we kind of split the difference and did a row at a time? So we're going to have 1,000 times less Go routines, but they'll each be doing 1,000 times more work. Is that going to make us faster? For comparison, let's just look at per pixel mode again, 1.8 seconds, and let's try this row at a time mode. That's looking better. We've almost cut that time to a quarter of what it was. We made it, while also apparently using more user time than we did real time. So there's probably some parallelism going on, and that's why we improved the speed of the code. Let's look at the trace tool. You notice how much faster that opened. It's because there's 1,000 times less Go routines, there's 1,000 times less interactions. And one of the nice bits about that is that the trace, we now get to see the whole of the program in the trace. We also see what we expected with Go routines. We get this, maybe I'll use magic. We get this large peak that we expect, like the producer is running ahead of the consumers, building up work on the scheduler. So at this point, we have 850 runnable Go routines, 600, 400. That's what we expect. We also, if we look at the number of threads, 8 are running. So there's 8 procs just chewing through that backlog of Go routines. We also see, I collapsed that, there we go. We also see that now we have work on each of our CPUs. The colors, by the way, are not indicative of anything. You don't get to control the color. It's not like what Patrick Hawley was suggesting yesterday. They're just assigned so that you can tell when 2 different Go routines are next to each other. So each of these boxes represents the time to start a Go routine and compute 1,000 pixels. And then at the end, we obviously collapse back into printing out the image. Okay. So that's pretty good. In fact, that's very good. If you look, the time to compute the image is about 200 milliseconds, and the time to write it out is about 200 milliseconds. Instead of this program being dominated by the time to compute the image and a little bit of overhead and writing out the image, it's now almost 1-to-1. Now, when I give this example in my workshop, usually people say, well, okay, you start 1,000 Go routines, that's fair, but what if instead we had just some workers and we fed them coordinates? So instead of starting 1,000 Go routines, we'll just have a worker pool and we'll feed them work to do. Is that different? Is that going to be faster? Are we still paying too much overhead in the scheduler? So we can investigate that. We have the time. So we start a number of workers we're provided, and each of those workers ranges over the channel, getting essentially a row, saying please compute this row, and then for every column in that row, calls fill pixel. So we say to the worker, please go and render that line, and you go and render that line. In the main Go routine, we queue up all that work, and we know we can queue it up because this is a buffered channel. So we've made sure that we have enough space that the producer, if it wants to, can run all the way to the end, set up all the work, close the channel so that those workers will eventually exit, and then just wait for them to exit. So instead of running each of them in a Go routine, we've kind of chosen to use a worker model. This is obviously the... So we now have the ability to control how many workers we have. Let's say 8, because that's how many CPUs I have. Mode workers. So just for comparison, this is the row, and this is workers. Pretty much the same. Pretty much the same. Let's have a look at let's quickly look at the trace. Just as a comparison, here is the per Go routine model. We can see each of the different Go routines. This G is the Go routine identifier that the runtime uses internally, so we can see that these are different Gs, kind of scheduled at random. If we look at the trace here, overall it's very similar. Let me just kind of, for comparison. It's very similar, but instead of this giant build-up of Go routines to service and then trailing away, it's just a fixed number of Go routines, which is our 8 workers. We see down here in the proc list that it's always the same Go routine, just doing work, getting another bit, doing more work. That's why they kind of clump together on the same line. This is G10, 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 G10. So one of the nice things is that we can see that they're not thrashing between CPUs. They live on the same CPU. They probably have all their data in the cache. Did this make much difference in practice? No, it's going to be quite difficult to get them on the same timescale. There we go. 0, 200, 400. 0, 200, 400. It turns out for this example, just firing off a bunch of Go routines or building the worker pattern gives about the same result. Like we have good CPU utilization. Which one is better for you? Like which one is more applicable? Maybe, I mean, depending on how this program is run, this work might be in response to some user input. Like this might be work you're doing as part of an API request or something like that. And so you may not want to dedicate all of the capacity of the machine to this request, lest you starve out the next one to arrive. So depending on your use case, you may want to dedicate a number of workers to computing this image and the other one in parallel with that. So I think I've shown that the two strategies deliver roughly the same performance, and it's really down to operational concerns of which do you want to do. This one with per Go routine is nice and simple. The worker one is a little more overhead of setting up the workers and waiting for them. But you can see that they deliver pretty much the same result. Now, obviously, if we have less workers, it takes longer. If we have too many workers, we don't really get any benefit. But you can see, while pprof couldn't help us out, the execution tracer showed us that we could bring more CPUs to use on this problem. And we improved the performance of the code, well, nearly 4 times. And what I want to end on, just as a little aside. So the worker model or the Go team model, it doesn't really matter. Obviously, the speed up in this program is coming from throwing more CPUs at it. So you could imagine, just imagine, Apple don't ship them yet, but if we had 16 cores, instead of 200 milliseconds, maybe that goes down to 100 milliseconds. We saw what happened when we throw one worker at it. It takes 1.6 seconds. So even though it isn't completely linear, you could make the argument that if we had more cores, we could reduce this runtime even further. In fact, you could probably take it to the logical extreme and say if we had 1,000 cores, we could compute each row at the same time. Now let's not get distracted on how much it's going to cost for 1,000 cores, but this problem is lends itself very well to parallelism. So imagine if we did. Imagine if we could compute every row in parallel. Imagine if we had 1 million cores. We could compute each pixel in parallel. We could effectively reduce the time it takes this to nothing. And the reason I mention this is you might have noticed the other part of this program is now the time it takes to compute the image, which used to dominate, is now 50% of the runtime. The other 50% is spent writing out a compressed zip of the image. And I can tell you that doing parallel zip is much harder than parallelizing Mandelbrot calculations. So overall, the runtime of this program is now dominated by how long it takes to print out the image. This is, although it jiggles between CPUs because it's doing writes, which is causing the write as a syscall. Sometimes it ends up back on the other CPU. But this is effectively now the sequential part of the program. And I mention this because of a very important law. And that is Armdale's law, which says that the potential speed up that you can achieve in a program is dominated by the sequential part of the program. Here, down here, this line here, this is the line that says, even if you have, you can imagine the sequence extending into infinity, but when this was proposed, I guess, in the 70s or 80s, the idea of 65,000 cores was considered to be infinite. But you can see that after 16, you get basically no benefit. There's no more speed up you can get. And that's with 50% of the workload being parallelizable. And we can see a visualization of that because we have 50-50 split here. You can see if we reduce this part of the program to nothing, it's still going to take you at least this long. And the thing I want to leave you with is to think about your own programs. Now, obviously, we want to use Go routines. We want to take advantage of the multiple cores in the machines. But think about your programs. How much of that work can be done in parallel? I mean, the example here, 95% in parallel. Only 5% of the program is sequential. And that still taps out at no greater than a 20 times speed up with 4,000 cores. So you think about your programs. They must do some argument parsing at the start. They must do a little bit of connection, a little bit of validation, reading a config, something like that. That's all coming out of your 5% of sequential work. So to speed up your programs the most that they can, the key is to make sure you can do as much work in parallel, and not just most of it, but effectively all of it. And with that, that's all I have for you. Thank you very much.